Can't. Unless I put something underneath it. All right. What? It's fine. Okay. Nicole, what do you got?
1.
Why?
Because they just moved around. They didn't go together.
Good. They didn't go together or split apart. What's this look like in this box here? A mixture of what?
Liquids and gases.
Liquids and gases. What about here?
Gases.
Gases. So that liquid evaporated. That's a physical change. Both of these boxes show a mixture of what? Elements or atoms. Good. What's this box show? Go ahead.
Okay.
What's this box show? Compound. Okay, that's one pure substance. It's a compound. 2 particles, but they're identical, uniform in composition. Those are compounds. 2 different colors touching. What happens here? What happened to the compound?
It's split up.
It's split up because compounds can be broken down chemically, right? This could be electrolysis. Now it's just a mixture of atoms, kind of like this. Okay? Mixture of atoms. They come together to make a compound. What's that called when you take 2 and form it to make 1? You're making something. You're forming something. It starts with an S. What is it? Say it. Synthesis, yeah. So this is synthesis. I'm not going to ask you about that tomorrow. I'm just going over it now because that's what's happening. So these 2 are coming together to make 2 compounds, 2 molecules, right? Don't forget that. Molecules are 2 or more atoms touching. They can be elements, like this one. That's an element, or compounds, because there's 2 different, right? So this one is a mixture of a diatomic element and a compound. And then what happens is these all combine to make super compound, okay? So you have a compound, you're adding these to make it a bigger compound with more particles, more atoms. So what do you need to know for tomorrow? Mixtures, elements, compounds, solid, liquid, gas, substance, pure substance versus mixture, like I said, physical, chemical change. These are all chemical, because they're breaking apart or coming together. And atoms and molecules, right? Atoms and then molecules. Make sure you know all of that. Hopefully you do. Questions before we move on? All right, take out your notes. Kayla, come on up here and take these back, please. 7. Okay. I just want to talk to you about a couple of those. If you have time after class, that would be good. Okay. Just take us 5 minutes, not even. All right, so. Okay, yeah, Devin. What period are you? You have first period tomorrow? Okay. So you are even. First period. Okay, so in our notes yesterday, we left off talking about conservation of energy. We wrote down what happens when you hold an ice cube, and then what happens when you hold this hot pack that was hot, it's not hot anymore. So let's reiterate what we talked about yesterday. What does that mean, reiterate? It means explain it again. Who wants to do that for me? When you're holding an ice cube, how does it show conservation of energy? Go ahead, Ryan.
It takes the heat from your hand and uses it.
Say it differently. You said it takes, when you say it, you mean the ice cube?
The heat energy in your hand to like help it change phases to like liquid.
Good, very good. Yeah, the ice cube uses that heat to change phase. Very good. I just want to say something. I'm kind of particular the way I say this here. Steph. Yeah, the heat moves from the hand to the ice cube. So let's talk about it in terms of where the heat's coming from. So everything you're saying is good. Let's just make sure we use the right terms. So the heat is moving from your hand into the ice cube. Why is that? Because cold doesn't exist, right? Said that yesterday? No? Did I use that phrase? I think I did. Cold doesn't exist, right? So what is cold?
It's just a lack of heat.
Right, it's a lack of heat. Okay, but we don't talk that way. We don't say, man, I have a lack of heat, right? I said that yesterday. Or it's a lack of heat out today. That's strange. You'll have no friends. Don't talk like that. But you still in real life say cold, but now you kind of should, maybe you already knew, but now you have a better understanding of really what that means. It means there's a lack of heat. Where's the heat going? Somewhere else, okay? That's usually colder. What? What does that mean? So heat always moves from areas of this to this. We wrote it. It's the last thing we wrote right at the end of class. Heat or energy moves from high temp to low temp, right. So when I'm holding this hot pack, Bree, what happens? Say it again? I still can't. You said the heat from the what?
From your hand.
From my hand.
It's transferring.
Let's try again. But I can't hear you.
Is it hot now?
Let's say it is.
Okay, well then the heat from the hot pack is transferring.
Yeah, I was referring to yesterday. Sorry. You're right. Now, anyways. Yesterday, this was really hot. So when I'm holding it, the heat, I feel the heat because it's coming from the hot pack going into my hand. Okay? So the moral of the story, understand, not just memorize, understand the concept here that if you have two things that come in contact and one is warmer than the other, the one that's warmer has all the energy. So that's the one that's going to get rid of it. Okay? So it's always from high temperature to low temperature, and that shows conservation of heat. Or energy. The energy from here isn't disappearing. It's going into the air, it's going into the table, it's going into my hand, so it's being conserved, right? It's not being created or destroyed. So eventually, what happens to the temperature of this? Let's say it's really hot right now. If I was to just hold on to this for the next like 4 or 5 hours, whatever, just held it, what would happen to the temperature of this slowly? It would what? Decrease, right. What would happen to my hand for most of that time? Temperature would increase in my hand, right? That should make some sense. So, if that makes sense, write this down. Okay. We have some water in a beaker. In here, we have 90 degrees Celsius H2O. This block that we put into the water is 200 degrees of, let's say, iron, Fe. And then the air is 20 degrees. I want you to describe all the different scenarios that are occurring in this little picture for heat or energy transfer. Where's the heat coming from? Where is it going? What's happening to the temperatures? So think about it before I call on anybody. Explain heat transfer, basically the law of conservation of energy. There's 3 different things we need to talk about. Am I in camera still?
Yeah,
Okay.
that block shouldn't flow.
It's magic iron.
Moving
Jake's right.
It hasn't floated. It hasn't went down all the way.
Thank you.
I can't do that.
There you go. Good job. The iron is more dense than the water, so it sinks. Not because it's heavier, because it's more dense. All right, who knows the scenario? There's three things that I want to talk about here. Someone tell me, where's heat coming? Where's it coming from? Where's it going? What's happening to temperatures?
The heat is coming from the iron, as it was like heated up before, and then it heated up the water. And
So
water
the heat from the iron block is going.
to the water.
Okay, let's write that. Heat / energy is transferring from Fe to H2O. What happens to the temperatures?
They increase.
Both of them?
Oh no, just the water.
Right. So the H2O temperature increases. The iron Fe temperature decreases. What else is going on?
understand.
The way I wrote that's a little confusing if you're not following me. I should have wrote from Fe to H2O, but I just drew an arrow. So from the Fe to the water. Jake.
If heat keeps being transferred from the iron to the water's gonna boil.
Okay, so the water might boil. Good.
And then it'll evaporate, and then that heat energy will go to the air.
All right, you guys are
Energy.
you're moving too far into the future. Let's just say initially what happens. You're right, all that's right, but let's say it's not boiling. We're here right now. It's still liquid, not boiling.
Well, the Fe is just going to keep cooling down since the heat is still transferred
Good.
to the water.
Why did I label air?
That's good.
Because
Steph.
Because the heat from the water is going to the air.
Right. The heat / energy from the Fe and H2O transfers to the air. So the air temperature will increase.
But wouldn't the water start boiling immediately? Since the boiling point is 100 degrees.
It might boil fairly quickly, yep. I'm not really worried about that right now, as you can tell. So, there's all different types of energies being transferred here. The iron to the air, the iron to the water to the air. Eventually, the whole system will have the same temperature. True or false? Let's sit there, even if
True.
it boils away.
Yeah, true.
True. So that really kind of shows conservation of energy, right? That eventually everything will kind of even out and balance out. It'll cool down or heat up. So why will it cool down or heat up? Transfer of energy, okay? These are pretty popular, these types of questions. They'll give you a picture or they'll just give you like a few sentences, like a question saying, okay, a piece of iron is dropped in water. The iron is 200, the water is 90. Which of the following describes the energy transfer? And then it explains, it has 4 choices, and you gotta pick the one that makes sense. Okay? Questions with this. What if the iron block had been negative 20 degrees Celsius? What if the iron block was colder than the water? How would everything be very different here?
Go
ahead.
The heat energy from the water would be transferred to the iron.
Right, and the air would also be giving it energy because the air is warmer. So just remember, warmer to colder every single time. All right, let's define the word heat. Oh, good thing I look at my notes. I forgot one thing I wanted to talk about. You know what? Let's hold off on that definition of heat. I forgot to show you a video yesterday. I want to show you now. You don't have to write any notes or anything. Just pay attention. But I'm glad I looked. So lights, please. It's actually on the law of conservation of mass, but it's a very good video because it talks about the conservation of mass in a way I haven't really talked about yet. Oh, and you do have homework. Temperature worksheet. So I'll get that to you at the end of the period. Yes, I know you have the quiz. The temperature worksheet's real simple. Okay, it's kind of blurry, but it's the best I could find. It's a really good video. A lot of other videos are junk. So here we go.
The law of conservation of mass states that in a chemical change, matter is neither created nor destroyed. It is only rearranged. For example, let's place 5 zinc and 5 sulfur atoms onto the 2 sides of a pan balance. The 2 sides balance because the contents of each pan are identical. Consider the reaction of zinc with sulfur atoms on one side of the balance to form zinc sulfide.
Okay, how many zincs do we have?
5.
5. How many sulfurs?
5.
5. When they come together to make zinc sulfide,
5 zinc atoms will react with 5 sulfur atoms.
how many zinc atoms?
5.
How many sulfur atoms?
5.
5. 5 and 5. So what this is doing a good job showing you is that if you start with, for example, 5 atoms of zinc, 5 atoms of sulfur, when they go through this synthesis reaction, yes, they're going to change all their properties. Why? Because now they're forming a new compound. but the new compound and the new properties are kind of separate from conservation of mass. The mass will still be the same. If you have 5 and 5, and you still have 5 and 5, even though they're together, the mass will stay the same. So this is kind of why, this is why I balanced equations yesterday. When I went over the homework, I would put big numbers in front to balance the equation. What does that mean? The number of atoms on both sides have to be balanced. That shows the conservation of mass, that you have the same number of particles on both sides.
With a tremendous release of energy to form 5 zinc sulfide molecules. The two sides still exactly balance. The total number of zinc and sulfur atoms on each side are still identical, demonstrating the law of conservation of mass.
So it's a really good video because not only does it talk about conservation of mass, but you see how a chemical equation kind of works out. But this is a good way to look at conservation of mass, maybe better than how I taught it the other day, because I focus on the masses, like 10 grams of this, 5 grams of that, and the mass has to be the same. But this is really what's happening. The number of atoms on both sides have to be equal. That's why the mass is equal. So I thought that was good video to show. Those of you who are confused with what I'm talking about with mass or balancing equation, let me show you a quick example. Lights, please. Yesterday, you do not have to write this. Yesterday, this was one of the homework problems, but I had to balance it. I have 1 Na here, 1 Na here, 2 Cl's, and only 1 Cl, so I have to put a 2 here, which means I have to put a 2 there. You might be confused, that's okay. But let me show you how it applies to that video. If I draw 2 NAs, so 2 circles, there's 1, 2, and I draw 1 Cl2, so there's Cl2, and now I draw 2 NaCls, what you see is that everybody is balanced. What does that mean? That arrow is like the middle of that pan balance. How many NAs here? 2 of them. How many here? 2. How many Cls? Atoms? 1, 2. How many atoms here? 1, 2. So it's balanced, which means the mass of the reactants has to equal the mass of the products because I have the same amount of both. Right? So 2 NAs on the left and 2 NAs on the right weigh the same. 2 Cls on the left, 2 Cls on the right have the same mass. Therefore, conservation of mass. So that's why I showed you the video, to look at it a little differently. Okay? So I'd forgotten, so sorry about that. I kind of out of order there, but that's all right. Okay, so back to energy and conservation of energy and heat. Let's define the word heat. The term heat. What is heat? Anybody have an idea? Zach, you have an idea? You talk about heat a lot.
Temperature raises up, and I just get heated.
You just get heated, right?
Yeah.
Okay, so what is heat?
Energy?
Yeah, it's a form of energy. Energy that is transferred from, from a system with a higher temperature to a system with a lower temperature. So high to low. High to low. And let's talk about how heat affects phase changes. Phase changes. Solid to liquid, liquid to gas, or you can reverse that, gas to liquid, liquid to solid. I left space there on purpose. Leave space there. So let's talk about ice, water. What's going on?
Mr. McCoy, you should move this back so you can see the whole.
What?
You should move it back so you can see. Because you can't see like not half the board.
What happened?
You really
Look at
should
it.
just move it.
Just move it back farther on the desk. Just move the stand. Now you can see way more. And then you gotta push it forward because you see the little bottom. See the bottom? Look at the bottom. You can see that.
What are you talking about?
There you go. Excellent. You can see the wood.
You guys should make a committee of you have good ideas. So you
No,
should
I
call your
don't.
committee. We have good ideas.
I think we should also be a private cameraman.
Professional athletes.
Cameraman.
should be able to
Cameraman?
steroids.
Yeah.
Anything else? Chemistry teachers, perhaps?
We could just do. We'll be like a universal. Like
You didn't show people how to do electrolysis too?
I could, yeah.
Ice to water vapor.
You should
How
do-
does this happen, and what role does the heat play? So, you hold an ice cube, it melts. Why?
Because the heat is stretched.
Shh. I want people to think. Why? Why, when you hold an ice cube, does it melt and turn into water? Okay, everybody can understand this at this point. The heat goes from your hand into the ice cube. Great. Why does that melt it? That's the chemistry behind it. Why does it melt the ice cube? How about Evan? Not sure? Isla. Good. Then what? Yeah, but why is it melting? Because it reaches its melting point. That's a good answer. I want more though. I'll leave you alone. Edwin. Not friction. Good try. Well, actually, you're close. You're close. Great. Yes, it makes the particles move faster. So what we're going to write, you can write it somewhere underneath if you want, but I'm just going to put it over here to the side. So when a substance absorbs heat, so underneath here, we're going to write absorbs heat. Because if you want to go from a liquid to a gas, got to absorb heat, right? To boil water, got to absorb heat, sort of. You're going to learn this year you don't need heat to boil water, actually. But most of the time, you need to absorb heat to have phase changes. So to go from ice to water, water to vapor, it's got to absorb heat. Everyone, I think, is on board with that. Does anyone know what that's called before we write this? What's that word? Who knows the word for releasing heat? Someone said it in here before. Starts with E.
Electrolysis?